This presentation introduces the Smart Bone Bank concept, a next-generation platform for bone regeneration. By combining patient-matched 3D bone grafts with digital technologies such as AI, data analytics, and advanced fabrication systems, Smart Bone Bank aims to transform the entire workflow of bone reconstruction. The objective is to deliver faster, safer, and more predictable bone regeneration for every patient. This slide compares Shimu bone with bio-os and conventional allografts across key biological performance indicators. Shimu bone initiates bone formation as early as the second week, showing clear and continuous trabecular structure, and achieves near-complete material replacement by 8 weeks. Its osteoinductive potential is high due to the synergistic effect of OCP and TBB, while immune response remains low. In contrast, xenografts show delayed bone formation and high residual material, and allografts exhibit variability in both remodeling and immune reaction. Overall, Shimu bone provides a faster, cleaner, and more predictable regenerative pathway. Here we visualize the performance of Shimu bone, xenograft, and allograft across multiple evaluation axes, including shape compatibility, absorption and replacement, bioreactivity, osteoconductivity, osteoinductivity, infection risk, supply stability, and clinical applicability. Shimu bone demonstrates a consistently high profile across nearly all categories, reflecting its balanced and comprehensive biological performance. Xenografts and allografts show strengths in specific areas but lack the uniformity and predictability required for next-generation regenerative medicine. This slide explains the material science behind CT bone and Shimu bone. Both technologies begin with alpha-T CP micron powder, which is transformed into OCP through acidic aqueous hydrolysis. CT bone is fabricated using 3D printing to create fully custom implants, while Shimu bone uses ceramic injection molding to produce standardized anatomical geometry, or SAG-based grafts. Together, these two fabrication pathways enable both custom-made and fixed-shape OCP-based bone grafts. This slide illustrates the broader ecosystem surrounding Shimu bone. Healthy bone data from a curated database, combined with AI-assisted internal structure design and high-precision fabrication technologies, enables the creation of patient-matched grafts with optimized biological performance. The integration of digital transformation, surgical navigation, and advanced manufacturing positions Shimu bone as a central component of the future bone regeneration workflow. This slide outlines the complete workflow for Shimu bone transplantation, guided by surgical navigation. The process begins with patient CT DICOM acquisition and references a database of healthy human bones. A navigation-based surgical plan is created, followed by injection molding of SAG-based Shimu bone implants. Navigation guides ensure precise osteotomy, accurate graft selection, and fine trimming during surgery. This workflow enables highly accurate and reproducible bone reconstruction. Here we shift to CT bone, a fully custom 3D printed bone graft created directly from patient CT data. The workflow integrates DICOM extraction, CAD design, STL conversion, and high-precision 3D printing. Combined with surgical navigation, CT bone enables precise anatomical reconstruction tailored to each patient's defect. This slide presents the CT bone workflow in detail. After obtaining patient CT data, a navigation-guided surgical plan is created. The defect is modeled in CAD, converted to STL, and fabricated as a custom implant using 3D printing. Navigation ensures accurate bone cutting and precise placement of the CT bone graft, resulting in highly predictable surgical outcomes. Finally, this slide shows how Smart Bone Bank integrates CT bone, Shimu bone, titanium mesh systems, and surgical navigation into a unified regenerative platform. By leveraging CT DICOM data, 3D fabrication technologies, and navigation systems such as Stryker OrthoMap 3D and Medtronic Stealth Station, the Smart Bone Bank ecosystem enables a fully digital, highly accurate, and scalable approach to bone reconstruction. This slide lists the key scientific publications supporting the comparative data presented earlier. These include histological evaluations of xenograft and allograft behavior, randomized clinical trials comparing commercial graft materials, and molecular studies on bone regeneration mechanisms. Together, these references provide a strong scientific foundation for understanding why Shimu bone and CT bone achieve superior regenerative outcomes.